Hi everyone, I'm Professor Bergasser, and in this video we're going to be talking about the motion of a pendulum. We're going to do a little case study on how pendula move. Pendula are very simple instruments. They're usually just a weight on the end of a string, and they have been used historically for timekeeping for a very long time. You can see pendulum motion in grandfather clocks and all sorts of timekeeping devices for musical instruments. They've also been used in the past for measuring the surface gravity at the Earth. Before we had more sensitive instruments for doing this, pendula were taken all around the world in order to measure how surface gravity across the Earth varies with location. And so it's a very interesting motion that we can analyze with the forces and equations of motion that we've looked at before. And so let's take a look and see if we can answer a very simple question, and that's what determines the actual period of a pendulum. So we're going to try two different tacks on how to solve this. The first tack is to look at this problem from a dimensional analysis perspective. So tack number one, dimensional analysis. And if you recall, dimensional analysis is when we look at the dimensions of the units of the quantities that are important in the problem, and we try to figure out a way of combining those quantities so that we get the dimensions of the units of the thing that we're looking for, in which case is the period. So, the thing we are looking for, we want the period, which has dimension of time, which indicate by bracket t. And now we have to identify the things that may be important in this problem. Well, there's not a lot of parameters in this problem, so let's just start writing down what we have in our diagram above. We've got the mass of the pendulum bob, which we'll call m, and that has dimensions of mass, so it's pretty straightforward. We have the length of the bob, which has dimensions of L for length. And we have surface gravity, which has dimensions of length over time squared. Now we also have an angle, so maybe the initial angle might be something that we look into to see if that matters. But remember that the angles are dimensionless quantities, and we can't really use those values for any kind of dimensional analysis because they're just kind of a constant number that gets thrown in there. We don't know how to actually solve for that one. So we're going to leave out any issues about the angle and just look at these three quantities here. Well, so we want something that has to do with time, and surface gravity has a time unit in it, so it's 1 over time squared. And so our first attempt could be that it's proportional to 1 over the square root of g. So let me write down those units over here. That's going to be dimensions of time divided by the dimensions of length to the 1/2 power. So we've got our dimension of time okay, but we've got to get rid of this dimension of length, and we can do that by multiplying by the square root of the length of our pendulum bob. So that's going to give us dimensions of length to the 1/2, and those cancel out, and we end up with the right dimensions of time. So to our first estimate, we have the period is equal to the square root of the length of the pendulum divided by the surface gravity. Perhaps more accurately, we know the period must have to be proportional to the square root of length over surface gravity, because we don't actually know any of the numerical constants with this dimensional analysis. But this provides some interesting ways of looking at what are the trends with the period with things like the length of the pendulum or the strength of surface gravity near the Earth. So now we have some insights from the dimensional analysis. Let's actually go through the full process of solving for this problem to see if we can actually get a numerical consistent value for the period. So we're going to go through our regular process, looking at the knowns, make some predictions, draw some force diagrams, and see if we can come down to an expression for what the period is. So we already know that the knowns of our problem, we wrote them down in the last slide, are the mass of the bob, the length of the bob, and the fact that we have gravity acting on here. And we might also have an initial angle at which we displace this pendulum. These are all things that we'd have to specify at the beginning. And what we want is the period of the pendulum p. Okay? And now let's make some predictions about what we think the motion is going to look like. Now, in fact, we have a very powerful prediction from our dimensional analysis that the period is going to be proportional to the length divided by the surface gravity. So our solution should have some form of that expression in it at the end. The other thing we can know about the motion is that this is going to be an oscillatory motion. It's going to go back and forth, and so something about the motion should have terms of sine or cosine in it, because those are functions that we know go back and forth in a cyclic manner. So that gives an idea, something maybe the position, the velocity, acceleration is probably going to depend in some way on the sine and the cosine. All right, so now let's go ahead and write down the force diagram. So the thing that's really moving is just the little mass at the end of the pendulum, and that's got two forces acting on it. It's got a mass to it, and it's near the surface of the Earth, so we're going to have to write down a weight for a force. And it's connected to the string, and so that means there must be a tension force acting on the bob, and that's going to be pointed back toward the connection point wherever the pendulum is actually held from. And then the angles that we want to draw in here is the angle at which the pendulum bob has moved over. That turns out to be exactly the same if we draw it relative to the bob here, or we draw it relative to the vertical axis of where the pendulum is connected. So that's where theta is. And so now we can use that information to draw a coordinate system. Now we actually have quite a little bit of freedom in the coordinate system here. This is a motion that oscillates back and forth at a constant radius. And so we may be tempted to use a polar coordinate system, and that's a perfectly valid option. For this problem, we're going to look at solving this from a rectangular coordinate system perspective, and we're going to use a rectangular coordinate system that is aligned with our gravity axis, so x and y in this direction. And in fact, I'm actually going to point x in the opposite direction, assuming that as it is increasing its angle this way, it is moving in the positive x direction in the same direction. Okay, so we can draw our forces on this. Obviously mg is pointed straight down, that's our choice. And the components of tension, we just have to think again about how we solve for sine and cosine. In this case, if the angle goes to 0, then the tension force is pointed straight vertically up, and so the component along the y-axis must be t times cosine theta, and then the component pointed back toward the center is t times sine theta. Okay, so now we've got our force diagrams in the components directions that we've drawn from our coordinate system. Let's go ahead and write our equations of motion. A sum of the y forces, all right, looking at the vertical ones, that's going to be t cosine theta minus mg, and this is equal to the mass of the bob times its y acceleration. And the sum of the x forces is just minus t sine theta, and this is equal to the mass times the x acceleration. And those are the equations of motion that I can write down for this bob. Now we have a problem because we have three unknowns, the tension force and the two components of acceleration, but we only have two equations. So we need one more constraint equation. And as I mentioned, one possible constraint equation would be the fact that it's moving in an arc, so it's maintaining a constant radius from the pivot point, and that will provide some connection between the x and y coordinates. Basically, x squared plus y squared is going to be equal to the radius of the length of the pendulum, L squared. That's a little bit of a tough constraint to work with because of all these squares, and you have to take square roots. So we're going to make another assumption here, and that's a simplifying assumption that the pendulum never swings to a great angle. So the maximum angle at which this pendulum swings back and forth is small, all right? And small being that it's very close to 0. There's very little displacement from the vertical axis. Now let's actually draw a diagram to see how that helps us out. So I'm going to redraw my pendulum here, but now with a very small angle. There's our mass, there's our angle theta, there's our side L. And the way I've driven my coordinate systems, this axis here is going to be x, and this axis here is going to be y. And we can see that this makes a nice triangle, all right? And in fact, the sine theta is just equal to the x displacement, and we'll actually change that to delta x over L, because that is a displacement in delta x. And if that sine theta is small, that means that this is small, and that means that the displacement x is much, much less than the length of the pendulum L, which, if you think about it geometrically, makes sense. If we look at the cosine of the angle, cosine theta, that's the y position over L. We can also use our Pythagorean theorem to rewrite y in terms of the other two sides. This is just the square root of L squared minus the x displacement squared, square root of that over L. And notice that I put delta x is much, much less than L. So this subtraction here is taking a very large number and subtracting a very small number, which case this actually doesn't make much difference. So at small angles, this is going to be very close to square root of L squared over L, or approximately 1. And that is going to be true for any range of which this pendulum is moving, as long as it's moving a very small range. And if that's true, then the y position is not changing at all, right? That cosine theta term is constant, so this side of the triangle is always going to be constant. So there's no change in y, and that means that we can assume that the acceleration is approximately equal to 0. And that gets rid of one of our unknowns. That's the constraint equation we're looking for in this sort of simplified frame. So let's rewrite our equations assuming that our ay term has gone to 0. So we get tmg, pardon me, merging my forces here. So t cosine theta minus mg is equal to 0. That gives us an expression for t, which is mg over cosine theta. But remember, I said cosine theta is approximately 1, so this means the tension is approximately equal to mg. And that makes sense because if the pendulum was not swinging, that tension force is just balancing the weight of the mass. All right, so let's take a look at this other equation. We've got minus t sine theta. Well, now we can put in minus mg sine theta. And we can replace our sine theta with our displacement is minus mg delta x over L. And that's equal to the mass times the acceleration of x. And the masses cancel. And if I rewrite this now in terms of what the calculus definition for acceleration is, right? Acceleration x is equal to the second derivative of x squared, and that's equal to minus g over L times delta x. So now we're left here with a differential equation, and we've got to figure out now how to solve this differential equation in order to ultimately get to our answer of what the period is. Okay, so we have this differential equation. The second derivative of x with respect to time is equal to minus g over L times the displacement. And the displacement, of course, is equal to the position in the x direction as function of time minus initial position. By the way, we can always choose to set this equal to 0 if we want, because we have that choice in our coordinate system. All right, so how do we actually solve this problem? Well, we can go back and look at one of our predictions, the prediction that the motion is cyclic in some way, and so is going to depend on sine or cosine. So we can actually make an educated guess of what the position as a function of time looks like. We can guess that that's going to be something like x, let me use consistent symbols here. We can say it's x of t is equal to some combination of a sine function and a cosine function, where I've inserted inside here a constant, which is the angular frequency, that will set something about the period. And of course, that's the thing that we're looking at for that oscillation. So how do we know that this is the right solution? Well, what we can do is we can take two derivatives of it and see if we can plug it back into our equation. and see if that's the same thing. So fortunately, the sine functions are easy to take derivatives of. We just have to be careful of our chain rule. When we do the a sine omega t, sine turns into cosine, but then we have to take out our omega because it's the time derivative of the thing inside here. So we get a times omega cosine omega t. And for the cosine, cosine turns into minus sine, so it's minus b, and omega comes out times sine omega t. And by the way, it's always useful to make sure that we've got the right units. I've multiplied out a omega here that has units of 1 over time, or really radians per time, and that gives us our time dependence on the derivative with respect to time. So at least we know dimensionally we're doing the right thing. I can take the derivative of this again. This is why sines and cosines are so easy, because they just flip back and forth between each other. Cosine goes to minus sine, and that brings out a second omega. So minus a omega squared sine t. And derivative of cosine is cosine, so we get minus b omega squared cosine omega t. Okay, now look, something very interesting has happened. We have an a sine omega t here and a b sine omega, cosine omega t here. It's exactly what we started off with, but in both cases they're multiplied by minus omega squared. So this is just equal to minus omega squared times our original x position. And we can go back and see that this looks a lot like this equation if omega squared is equal to g over L. So we have a solution to the motion of the pendulum as long as omega squared, which is this factor we put in the sine and cosine, is equal to g over L. How does it help us find the period? Well, remember our definition for circular motion. If we have omega as an angular rate, when you go 2 pi times around a circle, that's a full circle, the angular rate is 2 pi divided by the period of the motion. So that's the same case here. Omega is 2 pi over the period of the pendulum. And again, that's because we're going by pi, we'll go with a sign that goes right back to its starting point. But we have an expression for omega, which is square root of g over L. And so we can solve for the period by just flipping this around. That's 2 pi times the square root of L over g. Okay, so let's do some checks and observations about how this answer comes out and whether it makes sense. So let's first look at some checks of our units and our predictions. Right? In terms of units, we've got an expression that depends on 2 pi times square root of length over g. So we have square root of length, which is going to be measured in meters, divided by g, which is measured in meters per second squared. Those meters cancel, so that's square root of 1 over second squared. So that gives us units of seconds, and that is indeed the units of period that we're looking for. The other thing is we had a prediction that p was proportional to square root of L over g from dimensional analysis, and indeed that's exactly what's come out. And what we've been able to solve is what that proportionality constant is. It's just 2 times pi. That comes out from the definition of omega. All right? And we can also look at some observations here. The fact that our general solution works for our differential equation. It uses the sines and cosines, so we were able to confirm sines and cosines work. And we have two initial conditions for the motion, right? Originally I gave just the initial angle, but that's actually not enough. You need to have a second initial condition because we're looking at accelerated motion. It's very similar when we had constant acceleration. You had to specify the initial position, initial velocity. We'd have to specify both the initial angle and perhaps the initial angular rate, or the initial position and the initial velocity, all right, etc. We'd have to specify these initial conditions in order to solve for the full motion, and we'll need to specify at least two of them. So that all comes out just looking at how the period. Let's actually see how we can use that period expression to solve for the actual motion of a pendulum. So just as an illustration on how we would actually use this expression for a period, consider the case of the seconds pendulum. This is a pendulum that moves in one oscillation period in every 2 seconds. So it takes 1 second to go across one way and 1 second to go across the other way. And a valid question to ask is how long does this pendulum need to be in order to have that oscillation period of exactly 2 seconds? Now if you want to take a moment now to pause the video and solve this for yourself before I go on, please go ahead and do so. So let's go ahead and figure out how we can solve this by using our period expression. Period is equal to 2 pi times the square root of L over G. So we can isolate out our length by just multiplying or dividing both sides by 2 pi and squaring them. We'll get 2 pi over 2 pi, p over 2 pi squared is L over G. And then we can just multiply both sides by G to get our expression to solve. All right. And putting in our numbers, we've got 9.8 meters per second squared. We've got a period of 2.0 seconds squared, and we're dividing by 4 pi squared. And we can check our units first. The second squared cancels, so 1 over second squared cancels the second squared here, so that goes away. And 2 squared is 4, so that actually cancels out the 4. And it turns out that the surface gravity is almost equal to pi squared, so when you write this out, you get a value of 0.99 meters. And I don't need a parentheses here at the beginning. 0.99 meters for our answer. Now, you might be thinking that seems way too close to be a coincidence, and that's indeed the case. Back in the 18th and 19th centuries, it was proposed that the length of meter be defined as a length of a pendulum that has an oscillation period of exactly 2 seconds. And that's a somewhat more convenient measure of length than that was eventually adopted for the meter back in the 18th century, which was 1/10,000,000th of the distance between the equator and the pole. But it turns out that the use of a pendulum for timekeeping, while very convenient, doesn't necessarily give precision across the entire globe. Because our Earth is rotating, it's slightly oblate, and there's also features under the ground that causes the surface gravity to vary by up to 0.7% from location to location. And if your measurement requires a timing accuracy better than 0.7%, then the pendulum is actually going to give you a different answer if you make a measurement, say, in London than you do in South Africa. So this is a little historical fact about the pendulums, but this is also an example of how we can use the period equation to solve for the length or the surface gravity or whatever we're trying to look for this kind of system.